Conducting tube. A very long conducting tube has an inner radius A and outer radius B. The tube carries a charge per unit length negative lambda. There is a line of charge that lies along the axis of the tube, right like this, right through the middle of it, that has a charge per unit length lambda. Derive an expression for the electric field as a function of distance r from the center of the tube for three regions: r less than A, r greater than A but less than B, which is inside the conducting tube. Then sketch the electric field as a function of distance r. C. What is the charge per unit of length on the inner surface of the tube? And D. What is the charge per unit of length on the outer surface of the tube? Derive an expression for the electric field as a function of distance r for r less than A. So we'll construct a Gaussian surface. And that's, can you see the dashed lines there? We have a cylinder with radius r less than A, and it is centered on the line of charge axis so that it is concentric with the tube. The electric field due to the line of charge is perpendicular everywhere to the long surface of the Gaussian cylinder. So here's our Gaussian cylinder. What we're saying is the electric field is perpendicular at all points to that tube. It is zero through the end caps. Here's our end caps. The electric field is not passing through there at all. And then the surface area used in the left-hand side of Gauss's law, okay, that's where we're doing our surface integral, our closed surface integral, is the long surface area. What we mean by that is the area here. And that's going to equal 2 pi r, which is the circumference of an end cap and also the circumference of the tube, times the length of the cylinder. So the area for the left-hand side of Gauss will be 2 pi RL. So we start with Gauss's law. And let's work the right side first. The enclosed charge. Well, here I want to know the enclosed charge by the Gaussian cylinder of length L. Okay, we know we have a charge density of lambda. Okay, a linear charge density. So what is that equal to? That's equal to charge over length. So the enclosed charge will just be L times lambda, or lambda L. So that's our right side. Now when we do the left side of the equation, right, I think for the rest of the presentation I'm not going to go into how E is constant everywhere, so it comes outside the integral, and then you're just doing a surface integral over all the little bits of area, which would be the surface area of the object you're dealing with. So that brings us, this is the left-hand side of Gauss like we talked on the previous slide. That will be E times 2 pi r L. And now you divide through by 2 pi r L. The L's cancel, which is very nice. So we get the electric field is lambda over 2 pi epsilon 0 r. And where did that charge come from? It came from that wire that was going right through the middle of the cylinder. Now find the electric field where R is greater than A and less than B. So you construct a Gaussian cylinder with those properties, and that's within the conductor. And one of the properties of electrostatic equilibrium is when you're in a conductor, the electric field is zero. So you just actually have to write those words and say E is zero. So that's a gimme. Whenever they want the electric field and your Gaussian surface is within a conductor, electric field is zero. Now find the electric field outside the tube. So we construct a Gaussian cylinder outside the tube, length L, and first thing we have to do is find the enclosed charge. Now the enclosed charge, due to the wire going through it, is a plus lambda L, and the enclosed charge in the conducting tube, that's a negative lambda, that's the charge density, so its charge is negative lambda L. Add those two together, you get zero. We use Gauss's law. Since the integral of E dot dA is zero, the electric field is zero outside the tube. Sketch the electric field as a function of distance r. You want to have your electric field for the three different areas here. You plot your graph, making sure to label the axes along with their units. And this one's pretty straightforward, right? Because if you're greater than A, it's zero, so you draw that line in. And then you have a 1 over r dependence between 0 and r less than A. So you would just sketch that in. It's very hard to tell a difference between 1 over r and 1 over r squared, but if you're sketching this for the College Board, they're not going to worry too much whether the line was as you drew it here, or maybe it was like this. I mean, as long as you show this 1 over r or 1 over r squared dependence, you'll be okay. So we've drawn it just like that. And notice, they didn't ask you to put in values. Sketch doesn't mean put in values, but frequently the problems will say, sketch it, and by the way, add critical values, maxima, minimum, things like that. We know the electric field at this point because we can just substitute in R equals A into that equation. And then we list A and B, and we're done. What is the charge per unit length, which is lambda, on the inner surface of the tube? We're going to draw a cross-sectional view here to make this easier. And here's our tube. Here's our tube outside in blue, and here's the wire. The wire has a charge per unit length of lambda. Because when we drew the Gaussian surface here, the electric field was 0, that meant it had to have an enclosed charge of 0. Therefore, what's going on is the wire polarized the tube, so an equal and opposite charge per unit length must exist on the inner surface of the tube. So the answer to this is negative lambda on the inner surface of the tube. What is the charge per unit length on the outer surface of the tube? The tube started with a charge per unit length of minus lambda. The wire then induced a charge per unit length of minus lambda on the inner surface of the tube, as shown in the previous section, Part C. Conservation of charge mandates that the total charge per unit length on the tube remains a constant negative lambda. Therefore, since the negative lambda all moved to the inside, there's nothing left on the outside. So a charge per unit length of 0 exists on the outer surface of the tube.